So the experiment we are going to see today is a closed loop control of DC motor. Now if you recall the experiment that we did sometimes back, which is a open loop control of DC servo motor. So this was the setup that we did. This was an open loop control system. So what we did was we applied some variable DC power voltage here, and then we loaded this particular motor, and then we tried to find out what is the torque speed characteristics and back EMF versus torque characteristics or speed characteristics. So this was an open loop system, which means that if there is any error that is fed back to the system, it is not going to correct itself. So what we are going to do is we are going to create a feedback mechanism to it, which is nothing but a closed loop control system. So that experimental setup here, so this is the experimental setup now for the closed loop DC motor control system. What is that you have here is, it is a similar setup. You see this part of the network, that is you are having an input voltage here, and then you have the voltmeter and the current, and the motor is placed here, which is nothing but this particular motor, and the shaft of this is connected to this particular torque arrangement. But here, in addition to this, we are going to give a feedback control system, which will be a closed loop control system. There are two kinds of feedback control that you can give. Either it is a proportional control or it is a proportional integral control. Integral control we normally do not give because that is the most unstable system. So in this particular setup, we are going to give two different kinds of proportional control system and proportional integral feedback system. So again, what is our procedure here is, because of this closed loop system that you have here, whatever is the steady state error that you are going to have here, that will automatically gets corrected because of the feedback mechanism or the closed loop mechanism that you have when you are using this PI controller. But when you use a PI controller, the steady state error will not get corrected. It will keep on oscillating between that particular error. So I will go through the procedure as below. Before that, let me explain you what is this setup is. This is the DC motor that we are having, which we need to control, and then VA corresponds to the voltage across this armature, and then the armature current you have, and in order to drive this you need a power amplifier, right? So we have a power amplifier terminal, which is PWM controlled power amplifier terminals. So we will be connecting these terminals to this so that we drive the motor. Again, what will be the input of this PWM converter will be from this particular summation. This summation will have either the PI controller input, and this PI controller input has got another summation where there is an input from your pot, and at the same time there is the dotted line corresponds to the closed loop feedback. So the closed loop feedback, as I mentioned in the previous the speed torque characteristics of an open loop system, you have two discs on both the sides, and these discs will be dotted, and there will be a laser beam which will try to sense how much dots are getting rotated. So based on that, you have the square pulse getting generated, and those square pulse will be responsible for the number of pulses per revolution. So that is what you have it inside this optical sensor, and the frequency to voltage converter you have. So based on the current speed of your motor, that will be current speed or the armature voltage of your motor, that will be fed back as a to this particular summation unit, and the error will be fed back to the proportional controller. What happens to when an error is being fed back to the proportional controller, that will adjust its tunable voltage to this power amplifier, and this particular cycle keeps on repeating. Okay, and when you use a PI controller, the proportional Kp is the constant of this proportional controller, and Ki is the proportionality constant for this integral controller. The feedback gets much faster. So to explain you in terms of the block diagram, so this is the block diagram which represents the complete setup. What is that you have is, you have the set point, which we are going to you set this using this tachometer, this pot meter, and then we are giving it to a proportional controller here. So proportional unit is here, the error voltage is fed to the proportional unit, and this proportional unit is given to a gain adjustment. It is nothing but an amplifier which you can adjust your gain. So which is nothing but here you can set to different gains. It depends on whether you want a 20% gain, 50% gain or 100% gain. So you have a gain unit, and then from the gain unit we are giving it to the your motor control system. So this is nothing but your motor transfer function. So your motor transfer function is given here, and from the feedback it is again fed back to your internal summation unit. So the feedback is fed back to the internal summation unit based on the speed. Okay, so this setup is as given here. So let me start with the procedure of performing the experiment. Now what is that you need to do is, first you have to from the set point, from the set point, it's not required because already they are connected inside. From the proportional controller output, give it to the summation unit, and then the output of your summation unit give to the PWM input of the controller, and then from the output of your controller give it to the armature in series, and similarly the return path of your armature from here connected to the negative of your controller, and again from this frequency to voltage converter input you give it to the proportional controllers. From this you connect it to this one. Okay. Alright, so now we are in a position to start. Okay. So once I switched on, right, it is at different speed. So what we need to do is, first we have to set the speed here. So how can you set this particular speed is, you can, let us set it to 1000 RPM. So I am just setting it to 1000 RPM. Okay. Now I have connected it to a PI controller. When I connected it to a PI controller, when I move to the output speed, that will be an error speed actually. So when I am moving it to an output speed, so this is the actual speed of this particular motor, which is an error speed, and however time you take, because of the now the feedback is being given to the system, it will take very longer time because the oscillation will continue to take place and it will not reach your set speed at all. Okay. Now I am going to use a PI controller. So for using a PI controller, all I am going to do is I am going to connect this PI into this system, and then I also I am connecting it to this particular system. Now you could see the speed has changed to 1150, and then it will take some time. The feedback loop is taking some time, and this speed will settle down at 1000 RPM. We have to wait for some time. Okay. So this is the advantage of PI controller over P controllers. Now what is the procedure that you need to do? What are the things that you need to do is, you have to again be similar to the open loop DC servo system. You have to plot the speed torque characteristics, but here there will be multiple speed torque characteristics. In the sense, the speed torque characteristics when you have a proportional controller will keep on changing. It is not going to be a constant one. Whereas for an PI controller, when you do a speed torque characteristics, it will be a steady state characteristics that you will see. Now you can look at the system. It has taken some time. Our set speed was close to 1001 RPM, and here the speed that the system has settled is 1005 RPM, or I mean now it is 6 RPM, right? So that small amount of error will always be there. And now the procedure is, you have to change the speed, find the speed torque characteristics. So you will be plotting these two characteristics. One is the either you can have speed or armature current, it doesn't matter, speed torque characteristics, and back EMF versus speed characteristics. Okay. Now what is that you will do is, you will try to load this particular arrangement. When you load this, what will happen? When you load this, let me go back to the diagram. You are loading in this transfer function you are loading this uh, machine here. So TL represents the load torque. When you are loading, you are actually providing the load torque. What will happen when you are loading your machine? Obviously your current will increase, your armature current will increase, your torque will increase, and your speed will decrease. So this is what it has to happen, right? So what are the observations that you will be making is, you will first note down the armature voltage. Okay, you will note down the armature voltage, the voltage between these two terminals. Between these two terminals, you will note down the armature voltage, and then initially it will be in a free loose mode, right? It will not be loaded at all. You will monitor what is the armature current from this meter, and then what is the speed. Speed will be the set speed, actually 1000 rpm or whatever it is, and then these are the calculations you need to make. Now what you will do is, you will load your machine. You will put some torque towards machine. When you put some torque, what happens is, I am just adding, you can see that this current is increasing, right? So you have to, when this current is increasing, your armature voltage will drop because your speed is getting dropped. You can see here that from 1007 rpm, now it is 995 rpm or so. Yeah, it will keep reducing. So likewise, you have to completely repeat. You load it, and then you monitor all these three parameters, that is armature voltage, armature current and speed. You keep doing this completely for one kind of a P controller, that is P controller with 20% gain. Repeat the same experiment with 50% gain now. Again repeat the same experiment with 100% gain, right? This is only for P controller. Then what you will do is, you will include the PI also. Again repeat the same thing for 20%, 50% and 100%. So which means you will have 6 tables to make. Okay. So again I repeat, what are the 6 tables that you need to make? First, keeping the proportional controller, okay, with gain as 20%, you will provide a load torque and monitor the armature voltage, armature current and the speed of the machine. Okay. Then similarly you change the gain to 50% and then to 100%. So 3 tables are done. Similarly, the next set of 3 tables will be including the integral controller also. Again you will repeat. So there will be 6 tables, and you will be plotting the speed torque characteristics and back EMF characteristics for this particular experiment.